Okay, in this video we're going to talk about catalysis, really starting with the foundations. We're going to use a lot of the tools that we learned in the last section on multi-step rate processes and rate laws for those. For example, the pseudo-steady-state approximation will be very important in our treatment. But let's start by just talking about what is catalysis. So Oswald in 1894 said that catalysis is the acceleration of a chemical reaction by a foreign substance. And key to this is the idea that the catalyst is unchanged by the chemical reaction steps. And in nearly all cases, a catalyst actually works by stabilizing the transition states and or intermediates so that a large barrier, shown here, for the uncatalyzed reaction actually becomes a small barrier when you break it into multiple steps. So by stabilizing each of these intermediates, the catalyst enables a new pathway involving species that weren't stable before and usually brings those barriers down in the process. So there are many types of catalysts, and they usually fall into two main categories. Homogeneous catalysts are things that are going to be dissolved in the fluid with the reactants. Those can include acids and bases, and also organometallic complexes and enzymes, common examples of those. And you can also have heterogeneous catalysts, and those are a separate phase from the fluid phase reactants. And these common examples of these are metal surfaces, acid sites and zeolites, and metal oxide surfaces. So lots of different categories of heterogeneous catalysts. Both of these two things have their pros and cons. Okay, so for homogeneous catalysts over here on the left, we have intimate mixing and contact between the reactants and the catalyst sites. The sites typically are all well-defined entities. Research on these things a little bit more easy to conduct conclusions about the mechanisms and the kinetics of these catalysts. They typically have perfect atom efficiency because of the fact that they're in intimate contact. So every site is doing the same thing and accessible to the reactants to the same degree. Now, the cons of a homogeneous catalyst are that they are difficult to recover and separate from the reaction and product mixture at the end of the process. In many cases, these catalysts, especially for the organometallic complexes, they tend to degrade or deactivate under harsh conditions. They are often made from expensive metals. You know, of course, nature is an exception. Nature makes many enzyme catalysts out of rather inexpensive things. And of course, acid-base catalysis is not expensive reagents. But when we talk about the organometallic reagents, oftentimes you're talking about platinum complexes, iridium complexes, extremely rare metals in many cases doing these kinds of exotic chemistry. On the heterogeneous catalyst side, the advantages are that they are typically very easy to recover and separate, very amenable to flow processes because of that. The fluid reactants come in, they flow over the catalyst, and the products flow out with the fluid phase, and your catalyst is left behind as a fixed bed. They are robust under harsh conditions, particularly high temperatures, and that's very important for a catalyst because, as we will learn about general characteristics of reaction rates, typically they are strong increasing functions of temperature. Now the cons, a heterogeneous catalyst often has very poor efficiency. Heat and mass transfer can become severe issues, and a poorly defined and or non-uniform sites are typically a challenge, right? So you have lots and lots of different kinds of sites. Oftentimes only a few of them are actually kinetically active, and it becomes difficult because of that to study the mechanism. So what we're going to do now is move towards studying individual categories of these things. We're not going to have time to go through all of them, but we will talk a little bit about enzymes for the homogeneous catalysts. We will probably do a few examples of acids and bases. Maybe in some of the worksheets we will see some organometallic complexes. And for heterogeneous catalysts, we will probably do some examples of things on metal surfaces. If you take this class from Professor Flaherty, you will undoubtedly see catalysis in zeolites. So let's go and talk about enzymes. Okay, so enzymes are these remarkable catalysts in biological systems. So they are true single-site catalysts. You know, the genetic code makes the enzyme the same every single time. True homogeneous catalysts, in a sense, the well-defined sites. They have been shown to give as much as 10 to the 17-fold acceleration over the uncatalyzed reaction in certain cases. And in many cases, they can be extremely selective. That is to say that they make the same product over and over again. They often work at mild conditions. Of course, if you're going to be a catalyst that's going to work in vivo, you are going to have to work at room temperature or body temperature. These are catalysts that are typically working at very mild conditions. They often work with inexpensive metals, and so they really stand out as examples of the holy grail in catalysis, to do exotic chemistry with inexpensive metals at mild conditions in aqueous solvents. They often have built-in controls, things like allosteric mechanisms that can allow them to turn on and off the activity under certain pH ranges, in certain temperature intervals, or in the presence of certain signaling molecules. So some of them work on a specific substrate, and others are promiscuous or versatile. They can work on lots of different substrates with a key feature that they require, as opposed to a specific molecule. In an elementary chemistry class somewhere along the way, this idea of a lock and key, that the substrate fits into the enzyme like a key into a lock. And that idea, I think, is illustrative. Certainly there is some docking, some molecular interactions that have to match, but it fails to describe certain aspects of the specificity and promiscuity. There's an update to this picture of the lock and key called the induced fit mechanism, and this was proposed by Koshland. And this idea is that you have an enzyme that starts out in this state. There's no substrate bound. The substrate comes in, and when it binds to the enzyme gets distorted. Certain features, these little anthers here around the substrate, have bent, and also the substrate, you can see, is sort of distorted. It's no longer this perfect little peanut shape. Now it is. Now it has also been polarized and distorted. Now in this next step, you have a chemical step where the substrate actually gets transformed. So some chemical reaction has happened, and now it looks like a completely different thing. And the enzyme in the process also relaxes and prepares to expel that product in that last step. And now you're back to here. Okay, so we refer to catalysis. We refer in catalysis to cycles all the time. And the basic idea is that you start out with the enzyme, it facilitates a chemical reaction, and at the end, you end up with the enzyme back in the state where you started. Okay, so we went around the circle back to where we started from the enzyme's perspective, or from the catalyst perspective. But what has happened as we went around that cycle is we converted our substrate into our product. It's not a futile cycle here. There is some chemical potential or delta G driving force to make this thing go around this cycle, but the main idea is that the enzyme returns back to its starting state, and it's ready now to go around the cycle again. A summarized version of this mechanism, and we will make lots of these, try and take a diagram like this and write down the elementary steps. So we have the enzyme plus the substrate. They associate to make a enzyme-substrate complex, and then the enzyme substrate complex reacts in a chemical step to make an enzyme product complex, and then the product gets released. Okay, so the product gets released and it frees the enzyme up again. This is a true catalyst because it is regenerated in the last step. Now, let's begin to think about how we would construct rate laws for a process like this. What would the experimentalist see if you tried to track what is the rate of product formation? What you have here, remembering back to what we just did last week, is a multi-step reaction mechanism. We also know that somehow the amount of catalyst is not changing, because every time the catalyst does its job, it comes back to where it started in the beginning. Without knowing the relative sizes of all the rate constants, so remember in our previous lectures on the pseudo-steady-state approximation, in order to justify the PSSA, we had to think very carefully about the relative sizes of the rates in different steps. And it was only valid in certain cases. Now, in catalysis, and in enzyme reactions in particular, we can apply the PSSA to all of the enzyme states automatically. We don't have to know the relative sizes of these rate constants. So what would those pseudo-steady-state approximations look like? Well, we could write them down in the usual manner. We have an enzyme state, we have an enzyme substrate complex, and we have an enzyme product complex. And we could make the pseudo-steady-state approximation on any one of these species, and in fact, we will see that we can make it on two of them. Why can we do this approximation? Well, let's think about that carefully. In most cases, the total enzyme concentration is much, much smaller than the reactant concentration. And we know that this total concentration adds up to something much smaller than the substrate concentration. Now, the claim is that the pseudo-steady-state approximation, when this is true, is always going to be valid. As you go around the cycle, the catalytic intermediates are changing populations amongst themselves, but they never really change above this small amount. And we're making in the amount, tiny relative concentration, in the amount of substrate every time we go around the cycle, because at most we can change a fraction of this number in the relative populations. Okay, so let's think about it in terms of a hydrodynamic analogy, right? So suppose you have this giant dam, a giant lake behind a dam, I should say, and it's very deep and it's very long, going way back here. Okay, so here's my dam and here's my turbine, and the turbine is spinning, okay? And every time it spins, it lets through some water, okay? But when it goes through one revolution, almost like one catalytic cycle, it lets through this fixed amount of water, but the amount of water that it lets through is very small compared to the amount of water in the lake. And so the turbine spins thousands of times, and the level of the water just goes down imperceptibly. Okay, and that's exactly the situation that we have for catalysis because of this inequality. Okay, because the enzyme amount is very much smaller than the amount of my reactants typically, we will immediately be able to apply the pseudo-steady-state approximation because I can turn over many times. That enzyme can go around that cycle many times before it makes an appreciable concentration in the reactant amounts. And that means I can derive the rate at which the enzyme goes around the cycle in terms of the amount of substrate that I have at a given point in time, without thinking about how fast that substrate concentration is changing. It's the same argument for saying that I can think about how fast this turbine is going to spin as a function of the depth of the water, without thinking about the fact that when the turbine spins, it changes the depth of the water on this process in the same way that we can do for the catalytic process. So this is this argument that we will see in all kinds of catalysis applications. You can always fall back on the pseudo-steady-state approximation when you're unsure whether you can apply some others. There are advantages, of course, of looking at these rate constants carefully and seeing whether you can apply others, because sometimes they're a lot easier to apply than the pseudo-steady-state approximation.